All right, so now we're going to talk about independent and dependent events. And actually, it's really nice because their definition goes quite in line with what the word actually means. So an independent event, it's when these two events are happening and they have no impact on one another. They're not going to affect the probability of one happening. So this happens a lot when you got like a bag of marbles or a bag of M&Ms. And let's say you take a marble out of the bag, which then would change technically the probability of the bag, but then you put it back in, so it didn't affect the probability because you replaced it. That's one of the key words. You replaced it. You put it back in. Whereas a dependent event, it has the ability to affect the probability of the other events happening. So that's that situation where things are not replaced. You took a marble out of the bag, but you didn't put it back in, which changed the total number of marbles in your bag. So let's look at some examples. A jar contains 6 blue. Let me start writing this down. 6 blue. We got 3 red, 5 green, and 2 yellow M&Ms. Okay? So in total, we got 6 plus 3 is 9, plus 5 is 14, plus 2, we have 16 M&Ms total. Once a candy is drawn, it is not replaced. So it's not replaced, which means it's a dependent event. Okay? Find the probability of getting 2 greens. So we're going to find the probability of getting a green the first time and drawing a green the second time. And I kind of mentioned this earlier on, and means multiply. Remember those examples where you're having 2 girls and 2 boys, 3 girls and 1 boy? Well, here we're going to have drawing a green and drawing another green, okay? And remember, in this example, I'm not replacing them. So the probability of drawing a green the very first time, there's 5 green out of a total of 16, okay? Possible over total. And means multiply, so I'm going to have to multiply these 2 events. Now, that second green being drawn, you have to remember, things have changed, okay? You drew a green out and you no longer put it back in, okay? So now the new number of greens is 4. We had 5, we took it out, now we have 4. The new total, we had 16, we took 1 out, didn't replace him, we now have 15. Okay, so we have 5 16ths multiplied by 4 15ths. And I'll let you do the calculations on that. Using the same M&Ms, actually let's look at a version of an independent problem. Okay, so we still got 6 blue, 3 red, 5 green, and 2 yellow M&Ms. Once a candy is drawn, it is then returned to the jar. So it's put back, so it's an independent event. We have not altered the probabilities. So find the probability of getting a green and then a blue. Remember, and means multiply. So the probability of getting green from the get-go is 5 16ths. In this situation, we're having independent events because the candy is put back. I won't eat it, but it's put back. When it's put back, the total is still going to be a total of 16 candies. Now, the number of blue is 6. Once again, I'll let you multiply your fractions. All right, let's look at another problem here. So the problem reads, in a board game, 3 dice are rolled to determine the number of moves for the players. Let's think about it. Do these dice affect one another? No, they don't. So that means we're going to have some independent events. So what is the probability that the first dice rolls a 6, the second dice shows a 6, and the third dice does not? So the first dice, we need a probability of rolling a 6. Well, there's only 6 sides on a dice, and there's only one way of rolling a 6, so we have 1 6. Now remember, it's rolling one die, and then rolling another die, and then rolling another die. So because I keep saying that word and, I'm going to be multiplying. The second dice, it asks what's the probability of him also showing a 6, which is still 1 over 6. Now the third dice, he was actually what's going to be called a complement, and I'll do that in the next video. A compliment means actually the opposite. So like number 3 says, him not rolling a 6. Not rolling a 6 means rolling a 1, a 2, a 3, a 4, and a 5. So there are 5 different possibilities out of our total of 6. See, here's our possibility of rolling a 6 and rolling a 6 and rolling a not 6 on 3 different dice. So when you multiply these fractions together, you get 5 over 216, and there you go. 3 independent events. All right, last example, we're going to look at some dependent events now. So 3 cards are drawn from a standard deck of cards without replacement. That's our key that it's going to be dependent events. We're playing with cards, and we're drawing cards, and we're not putting them back, which is going to change the total, which is also going to change the number of cards each time we're drawing them. So we need to find the probability of drawing a diamond, and then a club. I think that looks like a club. And then another diamond in that order, okay? So the first probability, drawing a diamond. We know there are 13 diamonds out of the 52 cards. My key word was and. I'm drawing this and then that. Now, the probability of drawing a club. I have not altered the number of clubs that is in this deck of cards. There's still 13. However, the number that I did alter, because I'm not replacing these cards, is the total. I no longer have 52 cards in a deck of cards. Because I'm not replacing them, I now have 51. My last probability is the probability of drawing a diamond. So this is where actually I have a couple things changing. Because I drew a diamond that first time, there's no longer 13 diamonds. I now have 12 diamonds. Because I drew a card here, and then I drew another card here, and I'm drawing another card, and I'm not replacing them, my total also changed. I had 52, then I had 51, now I have 50. And I'm going to have to multiply all these probabilities together because I'm drawing a card, and then drawing another card, and drawing another card. And when you multiply them all together, you get 13 over 850.